We are Group 7, and today we're going to be talking about our gearbox design. My name is Ryan Sheffield, Vanessa Nuñez, Stephen Valencia, and Kevin Alvarez. Some of the possible applications of our gearbox include mainly industrial and environment and agricultural uses. This is mainly due to that we're transmitting 5 horsepower at very low RPM, so this gives us very high torque applications. Some of the possible applications is agricultural, such as this auger. We have constructional hoist, so this is if we want to lift some heavy equipment or some heavy material on the side of a construction site, or perhaps an industrial conveyor belt if we need to move some heavy machinery across the manufacturing floor. For the problem description, we had to have that the input shaft and the output shaft were parallel, so that reduces our gear selection. The sets had to be opposite. We had to have very high precision, smallest possible volume and weight. Operator room temperatures, and our input shaft is to be at 800 RPM, while our output shaft is at 25 RPM. Some of the gears that we learned about in class include spur gears, bevel gears, helical gears, worm gears, planetary gears. However, for our application, the gear set that suits us best is the spur gear.
So after we consider all the possible options, this was the first one. For this one, we actually used 3-gear trains, and for the smallest gear was 16, the biggest 64. And we actually did all the calculations following the AGMA procedure, and all of the gears were above one digit. However, we were unable to find the 64 gear tools in the catalog, so because of that, we changed our configuration, and this is our final concept. So for this one, we actually used 4 different stages, in which the small gear was 16 and the biggest was 32. Here are the factor of safety, and as the promise statement suggested, the gear have an opposite shaft movement.
So for our calculations, we started with gear 7 since it was the gear with the biggest load, which you can see here in our design. It's one of the smallest gears as well. So we understood that that gear had the highest load acting on it, and we started working towards our other gears. The highest loads that we found were on the gear 7, but it also had the lowest amount of hours for the life of that gear. The highest life was found on the second gear, which is 237,000 hours. For our shafts, we found that the shaft C had the highest normal stress capacity on it, and also had the last shaft having the biggest diameter to work with. The other shafts varied between 0.5 to almost 0.6 inches in diameter.
So although costs were not a factor in this project, we still had to choose our gears and shafts and bearings from the Boston catalog. So when we added all this up, it accounted for around $1,600. This doesn't take into account our housing that we still have to come up with, and any other systems that would go into the gearbox. Now, developing a maintenance program is very important to this gearbox, right? Because we need to be able to set up a oil change program for this, and then we can do this by actually using a laboratory that can analyze our oil and therefore tell us, hey, you need to change the oil every so often at this interval or whatnot. We also need to take into account the environment that it is operating in. If it's in a hot, dusty environment, it will require more maintenance than if it works in a clean environment where it is operating at room temperature. Also, periodic visual inspections are required for this gearbox. This is a SolidWorks rendering of our project. As you can see, gear number 2 is the one that would have the longest life compared to gear 7, which would have the shortest life. We were able to achieve a safety factor of 1. If we were to manufacture this or mass produce this for other applications, we would go with something a little bit more conservative with a higher safety factor. But in this case, since they wanted such a precision gearbox, we went with this. Another thing that could be mentioned is that we could add magnetic plugs to the actual design in order to collect metal shavings, and that would also assist us in our maintenance program. This project allowed us to work with different catalogs and different engineering standards that could be a global learning experience for us here in the group, and as well as designing a system from scratch. And it was a great learning opportunity for us.